Non-stationarity means that important features of a process change over time. That broad definition covers several different mechanisms, and confusing them can lead to misleading inference. We begin with deterministic trends, where the mean follows a predictable function of time. Later we turn to stochastic trends, where shocks permanently move the path. Keeping these two sources apart is essential for estimation, forecasting, and economic interpretation. A deterministic trend makes the conditional mean vary as a known function of time with unknown coefficients. A stochastic trend arises from a unit root and evolves through accumulated random shocks. A series may contain either type or both. Their graphs can look remarkably similar in finite samples, but their economic implications differ. Shocks around a deterministic trend are transitory. Shocks to a unit root become part of the future level. Let me write down the simplest deterministic trend. I model the series as a polynomial in time. It starts with a constant, then adds a term in time, and can continue with higher powers up to time raised to the power p, and finally a stationary disturbance for the temporary wiggles. The polynomial is the global trend. A straight line trend is the most common. Higher powers allow curvature, but they can behave wildly outside the sample, because the highest power eventually takes over. Under an additive polynomial trend with stationary errors, the expected value changes with time while the variance remains constant. Non-stationarity enters through the mean alone. A broader model can let scale change as well. For example, the variance may grow linearly with time. Once both mean and variance trend, conventional polynomial trend inference may change substantially. A plot of the mean cannot reveal this second source of non-stationarity by itself. When the trend is correctly removed, the autocovariance of y equals the autocovariance of the stationary disturbance. If the disturbance is independent over time, true autocovariances beyond lag 0 are 0. Yet computing sample autocorrelations around one global sample mean leaves the changing deterministic mean inside the data. The result can be autocorrelations close to 1, falsely suggesting long memory. This is spurious persistence, created by omitted trend structure. We estimate a polynomial trend by ordinary least squares, or OLS. The design matrix contains a constant and successive powers of time. The fitted value is the estimated trend, and the residual is the detrended series. This procedure is straightforward computationally. Its asymptotic theory is unusual because the regressors grow with the sample size, so the usual design matrix divided by sample size does not approach a stable finite matrix. Estimation here brings one genuine surprise. The coefficients do not all converge at the same speed. Because higher powers of time grow so fast, the coefficients on those higher powers are actually pinned down very quickly, while the intercept and the slope settle more slowly. Once I rescale each coefficient by the right power of the sample size, the estimator is approximately normal under independent errors. So I must never compare raw standard errors across different polynomial orders as if they sat on the same footing. For a fixed date, the fitted trend converges to the true trend at the familiar square root sample rate, even though its coefficients have different rates. This distinction matters. An individual coefficient may look numerically small because time is measured in large units, while the fitted trend can still be precisely estimated. Rescaling time to lie between 0 and 1 often improves numerical stability without changing the fitted polynomial space. Walled inference can test restrictions on the trend coefficients. For example, the null hypothesis that every slope coefficient equals 0 tests whether the series has no polynomial trend beyond an intercept. Under the stated conditions, The Wald statistic has an asymptotic chi-squared distribution with degrees of freedom equal to the number of restrictions. The covariance estimate must match the dependence and heteroskedasticity allowed in the disturbance. A pointwise confidence interval for the trend combines the fitted value with its estimated standard error and a normal critical value. Pointwise means that coverage is claimed separately at a particular date, not simultaneously for the entire curve. Drawing pointwise intervals and describing them as a simultaneous confidence band is a common error. Simultaneous bands require a different critical value, or a method designed for uniform coverage. The quadratic example contains an intercept, a linear time term, and a squared time term. The coefficient estimates are correlated, and the limiting covariance matrix can contain large entries. Sample size scaling offsets those entries. A joint test of no linear or quadratic trend evaluates the two slope coefficients together. Testing them separately can miss joint evidence and does not answer the same question as a two-restriction Wald test. Serial correlation in the stationary disturbance changes covariance estimation, but need not change the basic convergence rates. Under regularity conditions, OLS and generalized least squares can share the same asymptotic distribution for polynomial trends. In practice, one may specify an autoregressive moving average model for the errors, or use a heteroskedasticity and autocorrelation consistent covariance estimator. A conventional independent error standard error is not robust to serial dependence. Why do those unusual powers of the sample size appear at all? Polynomial regressors put heavy weight on the later observations, and multiplying by a high power of time blows up the variance of the weighted sums. That is the whole reason the normalization looks strange. But let me stress the practical point. A fast mathematical rate is not a license to keep adding high-order terms. Choose the order from plausible shape and stable extrapolation, not from what the algebra permits. Trending heteroskedasticity creates a more serious change. If the variance grows at the same polynomial order as the mean, the highest order trend coefficient may remain consistently estimable but converge more slowly. Lower order coefficients can cease to be consistently estimable because increasing noise overwhelms their information. A robust covariance formula alone cannot repair inconsistency caused by a fundamentally different variance structure. Detrending is not an automatic cure for nonstationarity. An omitted break can masquerade as curvature. A high-order polynomial can fit noise, and its extrapolation can explode. Serial correlation can invalidate simple standard errors. Trending variance can alter consistency. Before selecting a trend, examine residuals, test sensitivity to order and time scaling, and ask whether the deterministic path has a defensible economic interpretation. Centering and scaling the time index can improve numerical stability without changing the fitted polynomial space. Raw powers of a long calendar index can be extremely correlated and may produce ill-conditioned calculations. Using time divided by sample length or orthogonal polynomial bases makes estimation more stable. Coefficients then refer to the transformed basis, so marginal effects should be translated back before substantive interpretation. Let me leave you with one caution. A fitted polynomial is a model of a changing mean, not proof that the mean truly follows that shape. If the residuals look stationary and the specification stays stable, it can support honest inference. If persistence, breaks, or changing variance remain, the model is still incomplete. In the next lesson, I relax the fixed global shape and let the data trace out a smooth trend nonparametrically. So far, I imposed one global shape on the whole sample. Now let me ask a more flexible question. Can the observations near a given date reveal the local mean without my committing to a fixed formula? The model still writes the series as a smooth trend in rescaled time, plus a possibly time-varying scale, multiplying a stationary weakly dependent error. Smoothness takes the place of a specific polynomial order. A linear smoother estimates the trend as a weighted average of observations. A simple moving average is one example. Equal two-sided weights use observations before and after the target date. Equal one-sided weights use only the past and present. The weights sum to 1 so that a constant signal is reproduced. The chosen window determines which local variation is treated as noise and which is retained as trend. The Watson estimator uses a kernel to assign weights according to distance from the target date. Observations close to the target receive greater weight, while distant observations receive little or no weight. The estimate is a weighted local average. A kernel describes the shape of the weights, and a bandwidth h controls their spread. The estimator is non-linear in the bandwidth, but linear in the observed data once h is fixed. Bandwidth is the dominant tuning choice. A small bandwidth uses few nearby observations, follows local detail, and has relatively low smoothing bias but high variance. A large bandwidth pools many observations, reduces variance, and can miss curvature or turning points. This is the bias-variance trade-off. Choosing a visually pleasing line after seeing the outcome does not provide a reproducible statistical rule. Here, I want two quantities that pull against each other. The first is the bias, the systematic error. At an interior point, and for a symmetric second-order kernel, this bias is small when the true trend is nearly straight, and it grows with the square of the bandwidth. The second is the variance, the random error. It falls as I widen the window and as the sample grows, but it rises with the local noise and with long-run dependence in the errors. Both quantities drive my tuning and my confidence intervals. Balancing squared bias against variance produces the familiar bandwidth rate of capital T raised to -1/5 under the standard smooth trend assumptions. At this choice, the trend estimator converges more slowly than a parametric square root rate. The slower rate is the price of flexibility. It also means that ignoring first-stage trend estimation in later analysis can have consequences that would be negligible under a correctly specified finite-dimensional model. The scaling of time and bandwidth must be stated consistently. When the design uses t divided by capital T, h is measured on the normalized interval. A window containing a given number of dates corresponds to a bandwidth that shrinks as the sample grows. Confusing a fixed observation count with a fixed normalized bandwidth changes the asymptotic argument and can change how much smoothing is applied across samples of different length. Kernel shape usually matters less than bandwidth, but it still affects efficiency and support. A Gaussian kernel assigns positive weight to every observation, although distant weights become tiny. A compact kernel assigns exactly 0 weight outside a window. The Econometric kernel is efficient under a common mean squared error criterion. Equal weights are simple and interpretable, but simplicity does not make them optimal for every smoothness target. Confidence intervals require both local sampling variance and bias control. The variance involves the long-run variance of the dependent error process, not merely its one-period variance. One may estimate this quantity with a heteroskedasticity and autocorrelation consistent method. If smoothing bias is not negligible, a nominal interval centered on the raw kernel estimate can undercover. Undersmoothing or explicit bias correction can address this problem. Bandwidth selection may use plug-in rules or cross-validation. Ordinary leave one out cross-validation is designed around independent observations, while time series errors can be auto-correlated and heteroscedastic. A selection method should respect dependence, for example, through blocked validation or an adjusted criterion. A bandwidth chosen on one series segment may also perform poorly after a structural change, so stability should be examined. One-sided smoothers are necessary for real-time prediction because future observations are unavailable. A one-sided equal weight or exponential smoother typically has a leading bias proportional to h, which is larger than the bandwidth squared bias of a symmetric interior smoother. Carefully designed negative weights or local linear regression can remove the first-order boundary bias. Negative weights may look strange, but they serve a precise bias correction purpose. The exponentially weighted moving average is a one-sided kernel method that discounts older observations geometrically. It reacts to new information while preserving a smoothed history. Its responsiveness is attractive for monitoring, but it is not automatically an efficient trend estimator. The smoothing parameter and initialization affect the path. Real-time estimates should be evaluated as real-time estimates, not compared unfairly with two-sided smoothers that use future data. Spline smoothing provides another flexible approach. A cubic smoothing spline minimizes squared fitting errors plus a penalty on the integrated squared second derivative. The smoothing parameter balances fidelity and curvature. With little penalty, the curve approaches interpolation. With a very large penalty, it approaches a straight line. Between data points, the solution is cubic, its first two derivatives are continuous, and it becomes linear at the boundaries. In discrete form, the spline roughness penalty can be written using second differences. The estimate then resembles ridge regression, with a matrix that penalizes changes in slope. The Hodrick-Prescott filter is closely connected to this idea and became prominent in macroeconomic trend cycle analysis. Its convenience does not remove familiar concerns about endpoint behavior, tuning, and possible distortion of dynamic relationships among detrended variables. Residuals formed after nonparametric detrending are generated regressors. For example, the empirical distribution of estimated residuals contains an additional first-stage term that would be absent if true errors were observed. Ignoring this term can invalidate distributional inference. The impact does disappear for some functionals. Under suitable conditions, preliminary deterministic trend estimation does not change the limiting distribution of estimated error autocovariances. Robust trend estimation replaces local means with local medians or quantiles when outliers are a concern. A Hampel filter compares each observation with a moving local median and a robust scale estimate based on median absolute deviation. Observations far beyond a threshold are replaced by the local median. The threshold controls robustness. Aggressive replacement can remove genuine structural events, so flagged dates should be investigated rather than silently erased. Let me pull the threads together. Non-parametric estimation is flexible, but it does not remove assumptions. It moves them into smoothness, bandwidth, boundary treatment, and how I handle dependence. So a credible analysis writes those choices down and checks alternatives, keeps retrospective two-sided smoothing separate from real-time one-sided estimates, and carries the first stage uncertainty forward when detrended data enter later models. What I am after is an estimate I can interpret and defend, not simply a smooth line. Now let me put the trend ideas to work in RR. I will use daily adjusted closing prices for the SPDR S and P 500 exchange traded fund, which we call SPY, from the start of 2015 through the end of 2024. My aim is methodological. I want to compare a single global quadratic trend with a rolling local quadratic trend. Please treat this as an illustration, not a trading rule or an investment recommendation. The code downloads adjusted prices, removes missing observations, orders the dates, and creates an integer time index. It also takes the natural logarithm of price. Adjusted prices account for corporate actions in the data source, while the log transformation makes proportional growth easier to represent. Data provenance and retrieval dates should be recorded because online financial series may be revised or delivered differently by different providers. The global model regresses log price on a constant time and time squared using the full sample. Its fitted value is one quadratic curve chosen to summarize all dates simultaneously. The curve is smooth and easy to estimate, but it imposes the same shape across a decade that contains very different market conditions. A strong in-sample fit does not establish that the polynomial is a stable data-generating mechanism. The signs and magnitudes of the linear and quadratic coefficients determine the curve's slope and curvature. If the quadratic coefficient is negative, the fitted parabola has an estimated peak where its slope becomes 0. That calculation is descriptive within the fitted sample. Extrapolating the peak beyond the data can be unreliable because a quadratic eventually bends according to its highest order term, even when the underlying economic process does not. The fitted global trend is first obtained on the log scale. Simply exponentiating it returns a conditional median under a log normal interpretation, not generally the conditional mean on the original price scale. The code applies a simple sample-based correction using the average of exponentiated residuals. This correction is transparent, but it relies on stable residual behavior and should not be treated as universally exact. The local quadratic method uses a rolling window of 40 observations. At each eligible date, it fits a quadratic regression using only the most recent 40 days and predicts the trend at the current date. The first 39 dates have no complete window, so their local estimates are missing. This is a one-sided local procedure because it avoids future data and can, in principle, be computed sequentially. The rolling estimate adapts because its coefficients are re-estimated in each window. When recent prices change direction, the local curve can respond much faster than the global curve. That responsiveness is not free. A 40-observation window can make local estimates noisy and sensitive to individual events. A wider window would be smoother but slower. Window length plays the role of a bandwidth and should be tested rather than assumed. Within each rolling window, the code predicts only at the final date. This endpoint prediction faces the boundary problem discussed in the previous lesson. A local quadratic can reduce some boundary bias compared with a local constant average, but it may still be unstable when the window contains little variation or an abrupt event. Inspecting the design matrix and extreme fitted values is part of implementation quality control. The code applies a local back transformation correction based on residuals from each window. Because that correction is estimated from only 40 observations, it can vary from date to date. Reusing one global factor would impose stability instead. Neither choice is automatically correct. The analyst should explain the estimate on the original scale and examine whether conclusions depend on the transformation and correction method. On the log scale, near exponential price growth appears closer to a linear path. This often makes long horizon proportional movement easier to visualize. The global quadratic provides one broad path, while the rolling quadratic captures shorter movements around it. A plot should use different line types as well as colours, so the observed series, global fit and local fit, remain distinguishable in grayscale and for viewers with colour vision differences. On the original price scale, the same fitted log trends become curved after exponentiation. Visual gaps can appear much larger late in the sample simply because the price level is higher. Comparing errors only in currency units therefore emphasizes later observations. Log scale errors correspond more closely to proportional deviations. The appropriate scale follows the scientific question, not which graph looks smoother. The global and local fits answer different questions. The global curve asks for one low-dimensional summary of the entire historical path. The rolling curve asks what a short recent window suggests about the current local level and curvature. Their disagreement is informative because it reveals sensitivity to the assumed horizon. It does not show that one is the true trend and the other is false. Several checks improve the analysis. Repeat the rolling fit with 30, 60, and other defensible window lengths. Examine residual autocorrelation and changing variance. Mark periods where data are missing or highly unusual. Compare the quadratic with local linear or spline methods. Most importantly, avoid selecting a window after observing which curve best supports a preferred narrative. Tuning should be reproducible and linked to the intended horizon. A common error is to call the rolling local fit nonparametric, and then interpret each changing coefficient as a stable economic parameter. The procedure is nonparametric in the sense that local polynomials approximate an unknown smooth function. Individual window coefficients are tools for local approximation. Their values can be highly correlated and unstable, especially near boundaries. The fitted local level is usually more interpretable than the coefficients themselves. Scale also changes what the eye calls a trend. A curve fitted to prices emphasizes absolute movements, while a curve fitted to log prices emphasizes proportional growth. Transforming back from a fitted log trend requires care because exponentiation is non-linear and residual variance creates a retransformation issue. The chosen scale should follow the economic question and be stated before visual comparisons are interpreted. Real-time availability is another distinction. A centered local smoother uses observations on both sides of a date and is appropriate for historical reconstruction. A trailing rolling fit uses only observations already observed and can support real-time monitoring. The centered curve may look smoother and more accurate near past turning points, but it has used future information that a forecaster could not possess. This example demonstrates a disciplined comparison, not a forecast contest. The global model offers parsimony and stable historical summarization. The rolling model offers adaptability and a possible real-time interpretation. Both can fail around breaks, both depend on scale, and neither addresses a stochastic unit root by itself. The next lesson turns from smooth deterministic change to stochastic trends generated by accumulated innovations. A unit root creates a stochastic trend. Instead of returning toward a fixed mean or deterministic path, the series accumulates innovations, so one shock can permanently shift its future level. This feature changes variance forecasting and regression theory. It also explains why two unrelated trending series can appear strongly related. Our task is to distinguish persistent but stationary dynamics from a process located exactly at the boundary of stationarity. Consider an autoregressive process of order 1. y at time t equals phi times y at time t minus 1 plus white noise. If the absolute value of phi I is less than 1, shocks decay geometrically and the process is stationary. If phi I equals 1, the process is a random walk. Its variance grows with time. So no finite time invariant unconditional variance satisfies the stationarity requirement. The same idea extends to autoregressive moving average models. Stationarity requires every root of the autoregressive characteristic polynomial to lie outside the unit circle. A root exactly equal to 1 is a unit root. Factoring out 1 minus, the lag operator shows that first differencing can remove that root. The difference series may then follow a stationary autoregressive moving average model, provided the remaining roots satisfy the usual condition. Take a small example. Suppose the autoregressive part has coefficients 1.2 and negative 0.2. That polynomial splits into two pieces. One piece is an ordinary stationary factor, and the other is exactly the unit root, the factor 1 minus the lag operator. When I difference the series once, I remove that unit root, and I am left with a stationary autoregressive moving average model of order 1 and 1 for the change in y. A series that is stationary in levels is called integrated of order 0, or I0. A series that becomes stationary after one difference is I1. If two differences are required, it is I2, corresponding to a unit root with multiplicity 2. The autoregressive integrated moving average notation records autoregressive order, differencing order, and moving average order. Differencing order should be diagnosed because over-differencing can create unnecessary moving average behavior. An I0 series is mean reverting with finite time invariant variance under standard conditions. A shock has a temporary effect and autocorrelations decline. An I1 series has no fixed long run, mean in levels, and a shock permanently changes its path. Sample autocorrelations in levels often decay very slowly. These are population distinctions, but finite samples can make a highly persistent stationary process look like a unit root. Simulation makes the contrast visible. An autoregressive process with coefficient 0.9 wanders persistently but tends to return. Its autocorrelation function declines geometrically, and its partial autocorrelation function has the familiar autoregressive pattern. Setting the coefficient to 1 produces a random walk whose sample autocorrelations remain close to 1 for many lags. Visual evidence is suggestive, not a substitute for formal testing. A shock comparison is even more direct. Apply the same negative innovation to a stationary autoregressive series and a random walk. The gap between shocked and unshocked stationary paths shrinks as powers of the autoregressive coefficient. For the random walk, the gap persists because every future level contains the accumulated shock. This difference has substantive meaning when we interpret whether policy or market shocks are transitory or permanent. Stochastic trends create three classic inferential problems. Autoregressive estimates near 1 have unusual finite sample behavior. Conventional t-statistics in regressions involving unit root variables do not generally follow standard limiting distributions. Independent unit root series can produce high R-squared values and apparently significant coefficients, a phenomenon called spurious regression. Differencing or co-integration methods are therefore not optional technical refinements. The Dickey-Fuller test begins with an autoregressive model of order 1 and treats a unit root as the null hypothesis. One may estimate the model in levels, or rewrite it so that the change in y depends on lagged y. The coefficient on lagged y equals phi minus 1. Testing whether that coefficient is 0 is equivalent to testing whether phi equals 1. The test statistic resembles a conventional t-statistic, but under the unit root null, it does not have a student t-distribution, even asymptotically. Its limiting distribution is non-standard and depends on the deterministic terms included in the regression. Software therefore reports Dickey fuller critical values rather than ordinary t critical values. Using a standard regression p-value for the lagged level coefficient is a serious mistake. There are several deterministic specifications. A regression with no constant is suitable only when both drift and non-zero mean are implausible. A constant allows a random walk with drift under the null. A constant and time trend permits a deterministic trend under the alternative. Adding or omitting these terms changes both the interpretation and critical values. The choice should follow the data generating question, not whichever specification rejects. The augmented Dickey-Fuller test, or ADF test, adds lagged changes of y to absorb higher-order serial correlation. The tested coefficient on lagged y still addresses the unit root. Lag length may be chosen with an information criterion or diagnostic checks. Too few lags leave serial dependence and distort size. Too many lags consume power, especially in short samples. The selected rule should be reported. Failing to reject the unit root null is not proof that a unit root exists. Unit root tests often have low power against a stationary alternative, whose autoregressive root is close to 1. Rejection supports stationarity under the chosen deterministic specification, while non-rejection leaves the evidence compatible with a unit root. Confidence sets, complementary tests, and economic context provide a fuller assessment than a binary label. A random walk with drift contains both a deterministic linear mean and a stochastic trend. Its expected value changes with time, while accumulated innovations create variance that also grows with time. A sufficiently large drift can make the graph resemble a deterministic trend, even though shocks remain permanent. This resemblance explains why separating deterministic and stochastic trends is difficult in finite samples and why regression specification matters. The Beveridge-Nelson decomposition expresses an integrated process as a stochastic trend plus a stationary cyclical component. It helps interpret permanent and transitory movements within one model. The stochastic trend is driven by the long-run effect of innovations, while the stationary component captures temporary departures. The decomposition depends on the fitted dynamics, so its components are estimates rather than directly observed economic facts. Unit root analysis is a sequence of decisions. Plot levels and differences, consider plausible deterministic terms, choose augmentation lags, inspect residuals, and compare specifications. Then, interpret rejection or non-rejection in light of power and possible breaks. A break in a stationary trend can mimic a unit root, while a near unit root can evade rejection. The next lesson adds a stationarity test, with the hypotheses reversed. The Dickey-Fuller family places a unit root in the null hypothesis. The KPSS test reverses the logic. Its null is level stationarity or trend stationarity, and its alternative contains a stochastic trend. Using both approaches can be informative because each protects a different null. Agreement is especially useful. Failure to reject either test is not agreement. It often signals weak information or competing forms of misspecification. The KPSS model decomposes Y into a constant, an optional deterministic trend, a random walk component, and a stationary disturbance. The innovation variance of the random walk is the key parameter. Under the null, that variance is 0, so the random walk is constant, and y is stationary around the chosen deterministic component. Under the alternative, positive random walk variance introduces a stochastic trend. The statistic is built from residuals estimated under the stationarity null. Regress y on the deterministic terms appropriate for the test and form cumulative sums of the residuals. If the residuals are stationary, these partial sums remain relatively controlled after scaling. A stochastic trend makes them wander systematically. The test aggregates the squared partial sums and divides by an estimate of the residual long-run variance. Long-run variance estimation matters because residuals may be autocorrelated and heteroscedastic. A short or long lag truncation can materially change the KPSS statistic. The deterministic specification also changes its limiting distribution and critical values. A level stationary test and a trend stationary test answer different questions. Software settings should therefore be chosen explicitly and reported, not accepted as invisible defaults. KPSS. Critical values are non-standard because the statistic converges to a functional of Brownian motion under the null. Large values lead to rejection of stationarity. This direction is opposite to an ADF test, where a sufficiently negative statistic rejects the unit root null. Remembering the null is more important than memorizing a critical value. A p-value must always be interpreted relative to the test's stated hypothesis. Near the boundary, a process may be local to unity. Its autoregressive coefficient equals 1 minus c, divided by capital T, so it approaches 1 as the sample grows. Such alternatives explain why unit root inference remains difficult, even with substantial data. Tests are designed around this narrow neighborhood, and conclusions can be sensitive to persistence, deterministic terms, breaks, and sample span. Combining ADF and KPSS results creates 4 broad cases. Rejecting a unit root while retaining stationarity supports I0 behavior. Failing to reject a unit root while rejecting stationarity supports I1 behavior. Rejecting both may signal breaks, non-linearities, or specification conflict. Failing to reject both is inconclusive, often because the tests have limited power. This table is a diagnostic guide, not a mechanical classification rule. The empirical illustration studies daily adjusted SPY prices from the beginning of 2000 through the end of 2024, plus a recent sample beginning in 2024. It constructs log prices and daily log returns. Log prices are natural candidates for I1 behavior, while log returns are typically closer to I0. The comparison also asks whether conclusions change with the sample window. For log prices, the ADF regression includes a drift, and the KPSS analysis considers both level and trend stationarity. For returns, the ADF regression is run without a deterministic term, while the KPSS null is level stationarity. These choices reflect different empirical scales. A deterministic term appropriate for a price level may be unnecessary for a short horizon return series. In RA, the unit root workflow removes missing values, selects the deterministic specification, includes an augmentation lag, and may use an information criterion for lag selection. The KPSS routine then estimates the long-run variance using its chosen lag rule. Reproducibility requires reporting the package, sample dates, lag settings, and transformation. Merely stating that a unit root test was performed does not identify the actual test. For SPY log returns, the ADF test strongly rejects a unit root in both the full and recent samples. The full sample statistic is about -60, and the recent sample statistic is about -11.3, both far beyond their 1% critical value. These results strongly support stationarity of returns relative to the unit root alternative under the specified regressions. The KPSS return results add nuance. In the full sample, the statistic is about 0.40. It rejects level stationarity at the 10% level, but not at the 5% level. In the recent sample, the statistic is about 0.05 and comfortably retains level stationarity. The mild, full sample tension may reflect changing volatility or other departures from strict stationarity rather than a unit root. Taken together, the return evidence is consistent with approximate I0 behaviour while allowing time-varying conditional variance. Stationarity of the unconditional mean does not imply constant volatility, independence, or normality. This distinction is central in financial time series. A unit root test addresses persistence in the level or mean structure. It is not a general test of every form of temporal dependence. Sample choice can change conclusions because persistence breaks and volatility evolve. A recent sample offers local relevance, but contains fewer observations and lower power. A long sample improves precision, but may combine different regimes. One should not select the window solely because it delivers a preferred test outcome. Comparing pre-declared windows and explaining structural differences provides more credible evidence. Formal tests should be combined with plots of levels, differences, and residual diagnostics. Structural breaks can cause stationary processes to look non-stationary. Non-linear mean reversion can escape linear tests. Conditional heteroskedasticity can influence finite sample behavior. When evidence conflicts, consider break tests, alternative lag rules, and models that explicitly allow changing variance rather than forcing an immediate I0 or I1 label. Lag and bandwidth choices are part of the test, not neutral software details. Too few augmentation lags can leave serial correlation in an ADF regression. Too many can reduce power. The long-run variance bandwidth in KPSS creates a similar trade-off. Report the selection rule and check whether the substantive conclusion survives several defensible nearby choices. The main lesson is to use reversed hypotheses constructively. A. DF asks whether the data provide enough evidence to reject a unit root. KPSS asks whether they provide enough evidence to reject stationarity. Their joint pattern exposes ambiguity that either test can hide. The final lesson connects these ideas to the efficient market hypothesis and tests whether returns contain usable linear dependence. The efficient market hypothesis links information to how prices adjust. In its weak form, past prices and returns should carry no systematic linear forecasting power once I account for risk and transaction costs. Here, I want to walk you through the econometric tests of that idea. Everything I say is an academic discussion of statistical models and historical data. It is not trading advice, it does not predict future returns, and it recommends no financial position. Samuelson showed why properly anticipated prices should fluctuate unpredictably, while Farmer organized market efficiency around the information reflected in prices. The intuition is competitive. If a predictable profit opportunity is widely recognized, trading tends to incorporate the relevant information into current prices. Random price changes can therefore be a consequence of active information processing, rather than evidence that markets ignore information. Weak form efficiency concerns historical market information. Semi-strong efficiency adds publicly available information and is often studied through event analysis. Strong form efficiency includes public and private information and is the most demanding. These forms are conceptually distinct. Evidence about autocorrelation in past returns addresses weak form efficiency. It does not by itself establish or reject semi-strong or strong form efficiency. Behavioral finance emphasizes biases, limits to arbitrage, and institutional frictions that can produce departures from ideal efficiency. Modern empirical work therefore treats efficiency as a testable approximation rather than an all-or-nothing law. Statistical predictability may coexist with small economic gains after costs and risk. Conversely, failure to detect predictability can reflect low power. The hypothesis must be tied to a specific information set and forecasting rule. A simple random walk says that price at time t equals price at time t minus 1 plus a mean 0 innovation. A random walk with drift adds an expected change. Iterating the equation shows that current price equals the starting value, accumulated drift, and the sum of all innovations. The price level is I1, while its first difference is the innovation and may be I0. Expected returns need not be literally constant. They may vary slowly or respond to conditional risk. At higher frequencies, a constant or negligible drift can be a useful approximation. At quarterly or annual horizons, modelling expected return may be more important. Rejecting a zero mean return model is not the same as finding exploitable inefficiency. The benchmark should allow economically defensible expected return variation. These tests all lean on how strong a random walk I assume. The strongest version, which we call RW1, says the price changes are independent and identically distributed with mean 0. A weaker version, RGW2, keeps independence but lets the distribution shift over time. The weakest, RW3, asks only for 0 means and 0 autocovariances and allows other kinds of dependence. Each test I run has to be matched to the assumption it actually targets. Calendar time and trading time create another distinction. Under trading time, each observed return corresponds to one trading interval. Under calendar time, a Monday return spans more calendar days than a typical weekday return, so its conditional mean and variance may differ. Ignoring this difference can create apparent distributional changes. Most daily analyses adopt trading time unless stated otherwise, but the convention should be explicit. An autocorrelation test asks whether a return is linearly associated with its lagged value. Under RW1 and finite variance, each fixed lag sample autocorrelation, multiplied by the square root of sample size, is approximately standard normal. A confidence interval around 0 provides a single lag test. This result relies on the strong independent and identically distributed benchmark and can fail under conditional heteroskedasticity. A portmanteau test combines several autocorrelations. The box-Pierce statistic multiplies sample size by the sum of squared autocorrelations through a chosen lag and has an asymptotic chi-squared distribution under its null. The Young box version adjusts the weighting to improve finite sample performance. Lag choice affects the question and power. Testing many lags after inspecting the same data can also create unreported multiple testing. Small sample autocorrelations are biased, and normal approximations may be inaccurate. Modified denominators and explicit bias corrections can help in some settings. More importantly, financial returns often have changing conditional variance, so a test derived for RW one may reject because volatility is dependent even when return autocorrelations are negligible. Robust portmanteau methods aim to maintain validity under conditional heteroskedasticity. An autoregressive test regresses current return on a constant and p-lagged returns. Weak form unpredictability implies that all lag coefficients equal 0. A joint walled test evaluates this restriction. With heteroskedastic returns, the covariance matrix should be robust rather than based on constant variance. Statistical rejection identifies linear predictive content in the selected lag set. It does not measure whether that content covers risk, costs, or model instability. Variance ratio tests use a property of random walks. Under suitable assumptions, the variance of a k-period return equals k times the variance of a one-period return. Their ratio should therefore equal 1. A ratio below 1 is consistent with negative serial dependence or mean reversion over that horizon. A ratio above 1 is consistent with positive dependence or momentum. Overlapping returns require the correct sampling variance. Classical variance ratio inference is tied to stronger homoskedastic assumptions. Robust versions allow changing variance, and automatic procedures select or combine horizons to reduce arbitrary tuning. Under RRW2 and RW3, asymptotic variances reflect time variation and dependence in squared returns. The details matter because volatility clustering is common. A classical rejection can disappear when the statistic is made robust to heteroskedasticity. The SPY illustration uses daily log returns for a long sample from 2000 through 2024 and a recent sample covering 2024. It applies autocorrelation and Young box tests, a robust automatic portmanteau test, an autoregression of order 5 with a heteroskedasticity robust walled test, and classical and robust automatic variance ratio procedures. Comparing windows highlights possible changes over time. In the long sample, both the Young box and robust portmanteau tests reject joint zero serial dependence. The robust walled test for 5 lagged returns also rejects at the 5% level, yet the autoregression explains less than 1% of return variation. This contrast is crucial. A large sample can identify tiny departures from 0 that have limited economic importance and may not remain stable out of sample. Long sample variance ratios are below 1 across the reported horizons, and both classical and robust automatic procedures reject the strict random walk benchmark. The pattern is consistent, with some mean reversion at daily horizons. It does not identify a profitable strategy. The tests abstract from estimation risk, trading costs, taxes, market impact, and changes in the data generating process, all of which matter for economic interpretation. In the 2024 sample, the Young box, robust portmanteau, and robust autoregressive walled test do not reject zero linear predictability. Some classical longer horizon variance ratios fall below 1, but the robust automatic variance ratio statistic does not reject. The results therefore look closer to weak form efficiency in this recent window. The shorter sample also has lower power, so non-rejection should not be described as proof. Tests of market efficiency are joint tests. They combine an efficiency proposition with a model of expected returns, risk, information, and market frictions. A rejection may reflect misspecified expected returns or structural change rather than a durable inefficiency. A non-rejection may reflect limited power. Robustness across horizons, samples, and economically plausible benchmarks is more informative than one isolated p-value. This chapter's evidence supports a careful conclusion. SPY log prices behave approximately like I1 processes, while returns are much closer to I0. Some historical samples contain statistically detectable dependence, but its explanatory magnitude is small and its stability is uncertain. Econometric tests can quantify departures from a benchmark. They cannot convert historical correlations into guaranteed forecasts, and they should never be presented as personalized investment guidance.